Good afternoon, esteemed attendees. Thank you for joining me today for this Samsung Medicine ultrasound meeting on a weekend. I am Jong-min Lee, an abdominal radiologist currently affiliated with the Seoul National University Hospital in South Korea. In today's session, I will be discussing the topic of quantitative ultrasound with a special emphasis on its pivotal role in assessing hepatic steatosis. In my talk, I'd like to explain the basic physics of QUS tools developed by Samsung Medicine for assessing hepatic steatosis. Next, I will share the result of the previous studies and clinical trials in NAFLD patients at Seoul National University Hospital. Then I will close my talk by discussing potential clinical values and the future directions of QUS. Non-alcoholic fatty liver disease, NAFLD, is the leading cause of chronic liver disease worldwide. Over the last 2 decades, its prevalence has increased considerably with an estimated overall global prevalence of 25%. NAFLD represents a spectrum of disease with the majority at one end with only isolated hepatic steatosis. A fraction of patients can progress to more aggressive subset such as non-alcoholic steatohepatitis, NASH, advanced fibrosis, cirrhosis, and even hepatocellular carcinoma. As we all know, liver biopsy is the current reference standard for diagnosing NAFLD by assessing the excessive accumulation of fat droplets in the hepatocyte. However, because of its invasiveness and the possibility of sampling errors, non-invasive imaging tools such as ultrasound, CT, and MRI are widely used. In this table, you can see advantages and disadvantages of the 3 imaging tools which are commonly used to evaluate hepatic steatosis. B-mode ultrasound is widely used for evaluating hepatic steatosis. However, it is qualitative and subjective for assessing steatosis, and operator or calibration dependent, and shows modest accuracy for mild steatosis. CT is easy to perform, but is inaccurate for mild steatosis and has a risk of radiation exposure. Although MRI tools are the most accurate, they are expensive and has a limited accessibility. In routine clinical practice, B-mode ultrasound is the most commonly used imaging tool for hepatic steatosis. However, evaluation of B-mode images may be affected by different calibration settings, shows low sensitivity for mild steatosis, and relatively low intra and inter-observer reproducibility. In recent years, as you can see in this table, several QUS tools using radiofrequency data, including tissue attenuation imaging and tissue scattered distribution imaging TSI, have been developed and commercialized to overcome the drawbacks of B-mode ultrasound. There are 2 major approaches in QUS, either calculating attenuation of ultrasound or backscatter using envelope statistics. Then how can QUS overcome the limitation of B-mode ultrasound? The key is the use of raw radiofrequency data of ultrasound signal. Here you can see illustration of ultrasound RF to B-mode data conversion process. The grayscale B-mode image, which we usually see, is generated by several steps of post-processing ultrasound RF signals. And during this post-processing process, the loss or alteration of information may occur. On the contrary, as the raw RF data contain more information than B-mode images do without any loss or alteration of data, any changes in tissue microstructures can cause quantifiable RF signals. Therefore, quantitative analysis of RF data allows a more comprehensive characterization of tissue compositions. As you can see, these two examples of normal and significant hepatic steatosis case. Let me first explain how tissue attenuation imaging works. TAI quantifies ultrasound attenuation based on the degree of center frequency downshift along the depth. As ultrasound signal attenuation is more significant at the higher frequency component, center frequency shows downshift as beam propagates in the media. As you can see here, severe attenuation in the fatty liver results in a greater degree of downward shift of center frequency. The result of TAI is presented as attenuation coefficient with the reliability measurement value given as R-square value. In addition, the mean and median value of 5 measurements are also presented. Second, tissue scatter distribution imaging, TSI. TSI is a tool that quantifies the backscattered ultrasound signal distribution using envelope statistics, which can reflect backscatter concentration and arrangement. In the liver tissue, fat droplet can act as scatterers, and the shape of their envelope signals appear different according to the concentration and arrangement of these fat droplets, as you can see here. The distribution of envelope signals can be modeled by applying statistical distribution, which is Nakagami distribution. Nakagami distribution is a method for describing the probability density function of the envelope-developed RF signal. It can vary according to the concentration of the scatters, that is according to the degree of steatosis in the liver. And the shape of the envelope distribution can be presented as a Nakagami parameter. TSI is based on Nakagami distribution. Here are TSI images and corresponding histogram of the scattered background signals of various degrees of fatty liver. In patients without fatty liver, the histogram shows a pre-Rayleigh distribution with the Nakagami parameter below 1. But in patients with severe steatosis, the histogram shows the post-Rayleigh distribution with the Nakagami parameter larger than 1. The result of TSI presented as a scatter distribution coefficient, which is a Nakagami parameter multiplied by 100. In addition, same as TAI, the average and median values of 5 measurements are also presented. And let's talk about the previous studies and clinical trials regarding diagnostic performance of QUS in NAFLD patients at SNUH. For clinical adoption of quantitative imaging techniques, they should have high reproducibility. In our previous study, both TAI and TSI parameters showed excellent intra-observer and inter-observer reliability. In addition, both TAI and TSI showed a strong positive correlation with subjective visual grades of hepatic steatosis. Furthermore, both TAI and TSI showed a strong positive correlation with controlled attenuation parameter, CAP-based steatosis grades. And how about correlation with MR proton density fat fraction based steatosis grade, which is the most accurate non-invasive diagnostic tool of hepatic steatosis? Again, both TAI and TSI showed an excellent correlation with MR-PDFF based hepatic steatosis grades. Here are 4 B-mode images of the liver in 4 patients. Can you estimate how much fat is contained in the liver? This may not be easy, and there may be inter-observer variability among the radiologists. However, in these 4 patients, TAI and TSI can provide objective values for assessing hepatic fat contents in each patient, which correlated well with MR-PDFF values. In patients with clinically suspected NAFLD, both TAI, TSI showed good diagnostic performance for diagnosing various degrees of hepatic steatosis. We enrolled 173 patients with clinically suspected NAFLD patients. As you can see here, both TAI and TSI showed good diagnostic performance for various degrees of hepatic steatosis, although the diagnostic performance of severe hepatic steatosis is relatively lower than that of overall hepatic steatosis. It is probably due to saturation effect of QUS values in severe hepatic steatosis. Here, the scatter plots show that QUS values are saturated in severe steatosis. This saturation effect can be explained by the inherent limitations of ultrasound signals, which become weaker and more insensitive in severe steatosis, as it is already severely attenuated in the near field. In addition, we are performing multinational, multi-center clinical trial, including 3 Chinese hospitals, to evaluate diagnostic performance of TAI and TSI for evaluation of hepatic steatosis using histologic steatosis grade as a reference standard. TAI and TSI are non-invasive and easy to perform, and they enable more accurate estimation of hepatic steatosis. Furthermore, unlike conventional ultrasound, QUS provides continuous values related to hepatic fat contents. Now let's talk about the potential clinical values and future directions of QUS. In this context, QUS can be helpful as a screening method for assessing hepatic steatosis in a large population. It enables a more accurate diagnosis of hepatic steatosis, and it can be helpful for longitudinal follow-up and treatment monitoring by providing continuous and objective values. Moreover, a multi-parametric approach by combining TAI and TSI may allow comprehensive evaluation of tissue composition and can help select patients for an additional test, such as biopsy. More recently, Siemens and Samsung Medicine have developed the ultrasound-based fat fraction technique, USSF, which is a newer advancement in the field. The USFF technique employs a logistic regression model that considers both the attenuation and backscatter coefficient. This method presents the result as a percentage, as you can see here, making it easier to understand compared with the traditional attenuation coefficient. Here you can see ATI exam showing attenuation coefficient of 0.95, which suggests significant steatosis. However, QUS-based fat fraction shows 38%, which is definitely easy to make clinicians and patients understand regarding severity of hepatic steatosis. Then how about diagnostic performance of USFF? According to our unpublished research performed at 2 tertiary hospitals in Korea, we developed multiple logistic regression model using 173 patients from SNUH, and then validated the model using the data of 452 patients from Samsung Medical Center. QUS-derived estimated fat fraction, USFF, was well correlated with MRI-PDFF in both development and validation sets. How about diagnostic performance of USFF and QUS parameters for diagnosing hepatic steatosis? As you can see in this table, QUS-based fat fraction, USFF, showed better diagnostic performance for various degree of hepatic steatosis compared with QUS parameters. Indeed, both inflammation and fibrosis are also important histologic features of NAFLD, which can affect treatment strategy, like CAT and transient elastography and MR-PDFF and MR elastography. We can use both QUS and SIÅEW elastography together, which allow more comprehensive evaluation of inflammation and fibrosis as well as steatosis using ultrasound. Now let me briefly talk about future direction of QUS. Nowadays, AI or deep learning algorithms are widely used for improving diagnostic performance of imaging tests. QUS is not an exception. According to a previous study from UCSD, a deep learning algorithm using raw RF signal showed high accuracy for diagnosing NAFLD and quantifying hepatic fat fraction. Samsung Medicine and our team developed a two-dimensional convolutional neural network using B-mode images and parametric maps of TAI and TSI for hepatic fat fraction quantification. In our study, deep learning estimated ultrasound fat fraction showed an excellent correlation with MR-PDFF. Moreover, deep learning estimated hepatic fat fraction showed excellent performance for diagnosing various degree of hepatic steatosis when MR-PDFF was used as a standard of reference. However, further validation is needed as this study was performed in a single institution. In summary, Samsung Medicine's QUS tools enable quantitative assessment of hepatic steatosis. They provided a good diagnostic performance and reliable measurements, and they are easy to perform in routine clinical practice. Deep learning algorithm using QUS parametric maps can improve accuracy. Further validation is expected in various clinical settings. Thank you very much for your kind attention.